it's back. I can see now we have 27. So I think we can start because of time, because I have another class in the afternoon. So last time we were still continuing. Oh, this might be just 1 minute. I see whether this is the correct one. No, I have to upload. Let me just upload the correct one. Yeah. All right. Yeah, thank God. That's how we are. So last time we continued with the non-steroidal anti-inflammatories. We have now done the acetic acid. We have finished. Of course, we started with salicylic acids, did the phenamates. Then we were able to the acetic acid derivatives, where we had drugs in different classes like the sulidax, indomethacins, the todarax, and so on. Then we were able to move on to the other class of now the propionic acid derivatives. And we did mention that why these drugs are in different classes is because for the propionic acid derivative, the methyl group is very key. It introduces chirality. And for the propionic acid derivatives, it is the S-dextroisomer, which has more activity. And of course, we did mention that we give them as race meat mixtures, with the exception of naproxen, where we say we can also give the pure isomer. But we did also mention that the reason why we give them as the race meat mixtures is because the non-active, that is the less active, ad-livo-isomer is converted to the more active S-dextroisomer in the body using the coenzyme synthetase enzyme. And the biggest advantage is that once it is activated to the S isomer, it does not convert to the R isomer. And that is a very, very major advantage for these drugs. So we did look at quite a number of examples, and most of them are known as the profens. We did give different examples which had different characteristics. We started with ibuprofen. We mentioned whereby ibuprofen has an alkyl substituent as the second hydrophobic group. And then, of course, we did mention naproxen, where the two rings are fused together and therefore they cannot bring about coplanarity. We did mention phenoprofen, ketoprofen, and all these drugs. What is most important is that addition of a methyl group on the alpha carbon increases activity with introduction of chirality or stereochemistry, where the S-dextroisomer is much more active. And we did even mention that if you are to give the acetic acid derivative of ibuprofen, it has more toxicity and it has lesser activity, implying that introduction of that methyl group is of much, much importance. So we are done, of course, with the acetic acid derivatives, and of course we have nabumetone. Nabumetone, I don't think there's a M is there, nabumetone. And when you look at nabumetone, you can see it's a non-acidic. It can't fit in its own category of non-acidic as you give it, because you can't see this structure. Of course, structure is similar to naproxen in that at position 1, 2, 3. It has a 6-methoxy group as naproxen, as we had said that the 6-methoxy group at that position introduces maximum activity. But when we look at its group at position number 2, it is not an acetic acid, it is not a propionic acid derivative, neither is it an acetic acid derivative, it is a ketone. But indeed, nabumetone is a prodrug. Nabumetone is a prodrug, and in the body, it is converted to acetic acid derivative, which has activity. So we can classify as a non-acidic, non-steroidal anti-inflammatory. It has low potency, but it has the advantage of the fact that it does not cause gastric irritation, minimal gastric irritation, because as you can see, we did mention the reasons why you have gastric irritation is because of the nature of one of the reasons is the nature of the drug, because that drug is acidic. This drug is not acidic, and therefore you'll have minimal gastric irritation. Number two, when given like that, it is a prodrug and it is converted in the body to the active metabolite. Introduction to structure-activity relationship, introduction of the methyl or ethyl groups on the butanone side chain greatly reduced anti-inflammatory activity. So what we are saying is that when you look at this, this is 1, 2, 3, 4. That's why we're calling it butanone. So you cannot introduce any either methyl group here or anywhere in this side chain. If you do so, there is great reduction in activity. That's one of that. Then the ketone function can be converted to a dioxolane with retention of activity, whereas converting the ketone to an oxime reduced activity. We have looked at oxime, so I believe the structure of the oxime is quite clear in our minds. Sorry. Happened again. Dioxylane is a 6-membered ring with 2 oxygens. That's a dioxylane. That still retains activity, but with no added advantage. If you convert, whereas converting the ketone to an oxime, we have done a lot of oxime, double bond, NOH, all oxygen, that reduces activity. Removal of the methoxy group at 6th position also reduced activity, but replacement of the methoxy group either with a methyl, a chloro gave compounds that had activity. Remember, we did mention that those positions are a bit flexible. You can't change those groups with retention of activity, but so you cannot remove it, but you can replace it with other groups like methyl chloro with retention of activity. In other words, you're saying there it is not the specific group, the methoxy group, which is important for activity. It is the presence of a substituent, the right, an appropriate substituent at that position, which can be a methyl or it can be a chloro group with retention of activity. Replacement of the methoxy group with a hydroxy group, which is of course very highly hydrophilic, and acetoxy group, a bit more hydrophilic, and methyl carbamyl groups or positional isomers of the methoxy group that is at 2 or 4 positions greatly reduce activity. So we are saying yes, you can replace the chloro with a methyl. Those are still hydrophobic, but when you bring in groups which have extra oxygens and therefore introducing more water solubility, with the exception of methoxy group, then you will decrease activity. Again, we are saying you cannot change. You cannot give positional isomers. Positional isomers is where you change the position of this group. It requires to be in position number 6 for maximum activity. But as I had said earlier, the nabumetone is a prodrug, and in the body it is metabolized to give us 6-methoxy naphthyl acetic acid. 6-methoxy naphthyl acetic acid is closely related, which is closely related to the structure of naproxen, differing only by the lack of a methyl group. So this drug in the body, it is metabolized, it is not active, and it is not active. And when we say it's not active, we do understand, because it does not agree with the structural requirements for a non-steroidal anti-inflammatory, where we did mention there is need for an acidic center. Remember, the acidic center can be a carboxylic group, it can be a hydroxyl group, it can be a group that at least introduces acidity. This group, that drug does not have. It has a ketone, and therefore it must. And once it is metabolized, then it gives us the active metabolite, and the active metabolite is 6-methoxy naphthyl acetic acid, closely related structure to naproxen, differing only by the lack of a methyl group. The ketone precursor for 6-methoxy 2-naphthyl pentane 2-one. Can you try to draw this structure on your side? Just try to draw the structure for, then you have the substituent 6-methoxy 2-naphthyl. So at position 4 of the pentane 2-one, you have 6-methoxy 2-naphthyl, a substituent. Can you try and draw that structure? Can you try and draw that structure, class? Tell me when you are just a minute of doing it. 6-methoxy. So you can see I'm reading it is at position 4. So the main compound here is a pentane 2-one. Pentane 2-one. And but at its position above 6-methoxy 2-naphthyl substituent. I've made it very easy for you. The main structure compound we are looking at here is the pentane 2-one. At its 4th position of the pentane 2-one, you have the substituent 6-methoxy 2-naphthyl, 6-methoxy 2-naphthyl substituent. Have you been able to draw it? Say yes or no so that I can continue. Have we been able to, and we are not able to draw it, where are the challenges? Are we able to draw the structure 4? When you say 4, it is where the substituent comes in. And then you look at the main name. The main name is of a pentanone. Pentanone, of course, is a ketone. So pentanone is a ketone. So that ketone has a 6-methoxy 2-naphthyl substituent. How have we drawn it? Christine, thank you. Evans, yes. Anybody else? If you have not been able to draw it, where is the challenge? Where have we drawn? Let me get more responses, class. We said we will change. We will try to respond more. It's just to try. Even if you haven't got it, just try. Have you tried to draw that structure? You did UPAC. You did, I believe you did UPAC. I think UPAC, you do it in first year or second year. Organic chemistry. Yes, I can see more yeses. Have we drawn? Very good. So if this structure is not very hard, you draw the pentanone 2-one, the pentane 2. When you draw pentane 2-one, it means the ketone is at what position? Which position is your ketone in your structure? In your structure, your ketone is in which position? Again, let me get an answer. Ketone in which position? The ketone is carbonyl group or oxo. We call it carbonyl oxo, is in position number 2. Very good. So you draw a 5-membered pentanone. You have a 5-membered ketone. And at position number 2, you put your ketone or carbonyl group or oxo group. Then you go along that from position 1, you go to 2, you go to 3, you go to 4. At position 4, meaning you have left 1 methyl substituent. At position number 4 is where you draw a naphthyl ring, which has a methoxy group at position number 6. Let's get the structure, and if you got it right, please, if yours is correct, make sure you can give yourself a tick. If you didn't get it right, then ask yourself why. So this is what we are saying. This is the pentanone. This is a pentanone structure, position 1, position 2, position 3, position 4, position 5. But we are saying this naphthyl, the 6-methoxy naphthyl, is at position number 4. So did you get it right? Yes or no? So that is our structure. Now we are saying is that when this was given as a drug, the 4,6-methoxy 2-naphthylpentanone, it had no anti-inflammatory activity. And this was thought that it could be the precursor. It was thought that it could be also a precursor for naproxen. So it was thought to be a precursor for naproxen, but when it was given, it was found it does not have any activity. That's what all that point is saying, and it is emphasizing the earlier point, the point we did mention, that if you put either a methyl group or an alkyl group on that side chain, you destroy activity. So even this precursor, which was this drug, this compound, which thought to be the precursor of naproxen when it was given, it had no activity at all. So therefore, it had to be checked. This drug, this nabumeton, what is it converted to? And indeed, it was found it is converted to the 6-methoxy naphthyl acetic acid. The absorption and metabolism, I don't know whether I was jumped to one point. But before I get there, before we get to metabolism and whatever, let us now, we are looking, this is what we are looking at. So this is our nabumeton, and you have seen the structure. The structure, it has 1, 2, 3, 4. Nabumeton, it has 1, 2, 3, 4. It is a butane derivative. I bet that's where the bu came in from. So you can see it as 1, 2, 3, 4, not 5, 4. And nabumetron can undergo metabolism, and one of the metabolism it undergoes, it gives us a 6-methoxy naphthyl acetic acid. So you can see indeed it gives us an acetic acid derivative. So it gives us the acetic acid derivative, 6-methoxy-naphthyl acetic acid derivative. And of course, that is our nabumetron. It can also go whereby you have omega -1 oxidative hydroxylation there. And also you can get also the omega, this one of course already undergoing oxidative hydroxylation, and of course this undergoing oxidative O. So that becomes a hydroxyl group, and of course you have a hydroxyl group, and then these group compounds then undergoing glucuronic conjugation. You can also have nabumetron, of course, also undergoing oxidative O dealkylation. I think I'm very used to N. Oxidative O dealkylation to remove the methyl group, and that becomes a hydroxyl group, and of course that group is still retained. Some of these metabolites, I think, like some of the metabolites may have a bit of activity, but the one which was found to have maximum activity is the 6-MNA, which is a 6-methoxy-naphthyl acetic acid. One which was found to have maximum activity is the 6-methoxy-naphthyl acetic acid. So let us now look at absorption and metabolism of nabumetron, absorbed primarily from the duodenum, not from the stomach. You can't see it is not acidic. It's acidic drugs are better absorbed, a bit of them absorbed in the stomach, because acidic drugs are non-ionized in acidic media, so there will be good absorption. But when you have this drug, it can be absorbed in the duodenum. Milk and food increase the rate of absorption. Milk and food increase the rate of absorption, and the bioavailability of the active metabolites. If you discuss this drug, of course, in pharmacology, you look at that more. Pharmacokinetic properties are altered in the elderly patients with higher plasma levels of the active metabolite being noted, and therefore it implies that you will reduce the doses in the elderly. There will be dosage adjustment in the elderly because of the fact that the metabolite has higher concentrations. The major most active metabolite is the 6, we have already mentioned, methoxy-naphthyl acetic acid, but the initial alcohol metabolite, whereby initial alcohol metabolite, a minor product, and its ester, and its esters also possess significant anti-inflammatory activity. So we are only saying alcohol metabolites. You have this alcohol metabolite there, the initial alcohol metabolites and its esters are found to have some activity, but indeed the drug which has majority of the activity is the 6-methoxy-2-naphthyl acetic acid. And nabumetron is indicated again just for the same pains, fever, pain, and inflammation. I think with that, because we have also taken quite some time on this, we us now to finish the first category of the non-steroidal anti-inflammatories, where we have managed to mention quite a number of them. We have mentioned salicylic acid. In fact, we have mentioned drugs, apart from, of course, nabumetron, we have mentioned drugs that do contain the carboxylic acid. We started with the salicylates, covered the salicylates. We also covered the phenamates. I think then we went to the acetic acid, and of course the propionic acid derivative, and we have closed with nabumetron. I don't think, and of course when we looked at some of those drugs, we further classified them, and of course we did discuss some of them, though classified in a certain subclass, can be classified really as non-classical because there are some rules they did not obey, but they still brought some significant or some appreciable non-steroid or anti-inflammatory activity. So those are mainly the drugs that indeed do have a carboxylic acid. So we want to move on to the next category if we do not have any questions. Unless if we have questions, and I think we don't have any questions, then quickly, because of also of time, I'm taking too much time, we can move to the next category. And the next category of the drugs that we look at are the enolics. Remember, when we were looking at these drugs, at their structural requirements, we did mention they should have an acidic center. But we say it for most of them, they do have the carboxylic acid center, and that's what we have been looking at. We did mention also, we can have drugs that can undergo keto-inototemerism. When they undergo keto-inototemerism, it means they do have a ketone or a carbonyl group which can tautomerize into an alcohol. And once it tautomerizes into an alcohol, because of the structure, usually where you have electron withdrawing groups, the alcohol, because it's adjacent electron withdrawing groups, it can ionize in physiological media. Remember, these drugs must ionize in physiological media. And once it ionizes in physiological media, then that drug still has an anionic center or an acidity center. And that acidity center gives us an ionic center. And that anionic center will be able to bind to the cationic center that is found, to be able to bind to the so it has this, they will have an ionic center, so they will have an O-, and that anionic center will correspond to the anionic center that is found in the prostaglandins, and that would bind what we call the arginine cationic center that is found in the COX enzymes. Remember, we do have a positive center, which we did mention. It is because of arginine, and that positive center, which is in the guanidino moiety. The guanidino moiety is a protonated portion of the arginine. That guanidino moiety is a cationic center. So what these drugs must have an anionic center. It can be a carboxylic group, or it can be another group which can't be able in the body to give us an anion. And once it gives us an anion, that anion can bind to the cationic center within our enzyme, the COX enzyme. So that is why that's what is very important, and therefore we are calling these enolic drugs. And these enolic drugs, again, we can further subdivide them into two categories. We have the oxycams, where we have examples of meloxicam, piroxicam, isoxicam, and so on. And then we have the pyrazolones. We have the pyrazolones, and the pyrazolones, we have two categories. We have almost two categories there. We have examples like phenylbutazone, and we have dipyrone. So these are drugs that can undergo keto-inototemerism, and that's why we are calling them enolics. They are keto-ino. They have ketos and inos. Keto-inototemerism, and this is a kind of structure. We did mention this when we were looking at the tetracyclines, and all we are saying is that if you have this position here as an oxygen, as a hydroxyl group, this here can come in there. So there is a bond between oxygen and hydrogen. Do remember, this hydrogen has much higher electronegativity than compared to hydrogen. Remember also, this oxygen, highly electronegative, pulling away electrons towards this side, and therefore this hydrogen is quite naked in terms of has very low, is deficient in electrons, and therefore this hydrogen can be lost as a proton, and therefore the drug becomes a proton donor and hence an acid. And those electrons that are left behind can come in to form a double bond there. When they form a double bond there, then this carbon will have more than enough bonds, so this has to move out. It moves out, comes in here. So if you have your double bond there, that moves out, and it allows for an alcohol. So there will be an exchange. This will become the ketone, and that will become an alcohol. And in so doing, just as we explained with the tetracyclines, keto-inototemerism facilitates or allows for acidic properties, and that's why these drugs will be able to act as non-steroidal anti-inflammatories. So we start with the oxycams, and we have examples. And if you look at your handout, I know I have meloxicam and piroxicam. So look at your handout, go to page 15. Mine is page 15. And if you look at page 15, you will see the structure of piroxicam and the structure of meloxicam. So what you can draw, which you can also draw can draw is this other one. So we have piroxicam is there on page 15, and meloxicam is also there on page 15. So what you can draw is the tenoxicam. You don't have to draw the whole structure. Okay, this one you might have to, because it is a thiophene ring. So you can see that is tenoxicam, that is meloxicam. So if you look at our prototype, the prototype in this class is the piroxicam. And if you look at piroxicam, it has a benzothiazine ring. That's a benzothiazine. That is a sulfur. That's a nitrogen benzothiazine ring. You can't see what we are talking about here, allowing for ketoino-tautomerism. They are allowing for ketoino-tautomerism. And then for piroxicam, you find there is a pyridine ring. The pyridine ring is the one which is attached to the carboxyamide. This is the carboxyamide. That's a nitrogen. You have the pyridine ring. If you look at all just structural derivatives of piroxicam, you're looking at piroxicam is a prototype. It is, so if you can have isosteric replacement of the benzo ring, remember last time we said isosteric is where the electronic arrangement is almost the same. So you can replace, remember you were talking, we did mention that you can replace the aphenyl ring with a thiophene ring. Thiophene, you are still maintaining aromaticity. It's only that it's a 5-membered ring and this is a 6-membered ring. They are isosteric. If you look at everything else in tenoxicam and in piroxicam, it is the same. It is only an isosteric replacement of the benzo ring with thiophene. Then again, piroxicam, you can do again isosteric replacement, but this time of the pyridine ring. So that's a pyridine ring. You do an isosteric replacement, and the first isosteric replacement, again, remember this ring. We looked at this ring. This is a common ring to us. We did mention it a lot when we were looking at the antibiotics, the cephalosporins rings, the thiazole ring. So again, isosteric replacement of the pyridine ring with a thiazole ring with even better activity. So that again is, if you look at the structure, very similar to piroxicam. Then you have isoxicam. Again, we have looked at this ring, isoxazole. We have just finished with the oxa. I think we did mention the oxazole, and the oxazole, when we were looking at oxaprozine, we said the nitrogen and oxygen are separated by a carbon. If you talk about the oxazole, like here, the oxygen, nitrogen, as I said earlier, are next to each other. That's what makes a difference. So again, this is an isosteric ring, or it is isosteric to the pyridine ring, again with retention activity. What would you think from now looking at this, especially the isoxicam and piroxicam? What would you think would be the major difference between isoxicam and piroxicam? What would you think would be the major difference in terms of effect, negative or positive? What would you think would be the major difference in pharmacological effects when you compare isoxicam and piroxicam? Do you think there would be any difference in the pharmacological effects, whether positive or negative, between piroxicam and isoxicam? Would you expect there to be some differences in the reactivity of isoxicam and piroxicam? So when you look at, again, as you think about that question, and please give me some response, do you think there will be any difference in the reactivity between isoxicam and piroxicam, and why? So as you think about that question, and please put an answer. So again, you look at lonoxicam. Again, lonoxicam is a structural analog or structural derivative of tenoxicam, whereby there is also substitution of a chloro group on the thiophene ring. So lonoxicam, there is further substitution of the thiophene ring with a chloro group. So if you look at this, there is a lot of structural similarity. You're looking at the prototype. The prototype is piroxicam, and all the others are just structural derivatives of piroxicam. Us that there are certain groups within these drugs that must remain, that the pharmacophore, there is an area that you do require as the pharmacophore of these drugs, and you change that area and you destroy activity. Just as we have said with all the other drugs, including the tetracyclines, all the other drugs, each and every drug has its own pharmacophore. The pharmacophore is that area within a drug that you do require for that drug to bind the receptor. You change that area, you destroy activity. Also, another is one more example, and do have one other example. And if you look at this drug, I think dorixicam. If you look at this drug, the only difference between this drug, you can see this was our hydroxyl group here, OH. All that has happened is that the hydroxyl group, the oxygen of the hydroxyl group, is part of a heterocyclic ring. We have seen that severally, that sometimes a part of the drug, a part of even of the pharmacophore, can be part of the ring with retention of activity. But you can see here, when that happens here, we are creating an ester. You know, esters are highly susceptible to hydrolysis. So this drug, definitely, this drug is acting as a prodrug in the body. It will be cleaved here, and once it's cleaved there, it will give you piroxicam. So we are also saying that the oxygen of the 4-hydroxyl group can be part of a heterocyclic ring with retention of activity, giving us a prodrug, which in the body is metabolized to give us piroxicam, which indeed is our active drug. Have I gotten any answer? Umenyamaza kabisa. Have you given me the answer?